right. So, quick little logistical announcement here, right? I've had up on the screen. The first midterm is going to be next Friday. Few frequently asked questions. Let me see if I can preempt them. The exam is going to be 2 hours. It is designed to be a 50-minute exam. It's going to be the same length as an in-class exam that should take 50 minutes, but we're giving you 2 hours with the idea that we don't want time to be like the deciding factor. Okay. It's going to cover chapters 1, 2, 3. So for study guides, I recommend looking back on Icon and finding this course learning objectives sheet, making sure you're up on all of these tasks for modules 1, 2, and 3. You can do these things. Additionally, I'm going to be, after class today, I'll be posting a practice exam. It was the exam I used last year. You guys will have that for the next week. Sometime next week, Tuesday, Wednesday, or Thursday, I'm going to hold an evening review session. The idea is it's very much student-led in that you guys bring questions that you have about the practice exam, homework problems, etc., and I'll just work those problems on the board for about 2 hours. Okay, so it's going to be Q&A driven. You guys don't bring questions, I'll pack up and leave early. So that's going to be the format. The schedule for that hasn't been set precisely because I want it to be sort of what suits the majority. I know we're getting into midterm season here, so I want to avoid conflicts if possible. So I posted it on Icon already. If you go to Icon modules, exam 1 supplement or prep material or something, there's a link to to indicate your availability. And sometime tomorrow afternoon, evening, about 24 hours from now, I'll go ahead and request the room so that we have a space to meet. In terms of materials you can bring with you, right, shown here, organized binder with homework solutions, quiz solutions if you have, which are the same as the homework solutions, right? You can bring a handwritten summary sheet with formulas. This is one sheet, front and back, okay, that has formulas for chapters 1, 2, and 3, and a calculator. Things you should not bring are the actual, like any of the slides that I've posted, lecture notes themselves, or the book. The idea here is I've seen it too many times where people, right, students will bring too much material and spend the whole exam searching through it. So the idea here is summarize the equations you've learned over the last couple of weeks onto a sheet front and back, and then bring your worked problems. Rework those problems if they're ones that gave you trouble in the past. Yeah?
What about like specific properties?
So for like fluid properties, moments of inertia, for the hydrostatics stuff, those will be given to you, right? I'll give you there will be a couple of sheets at the front of the exam that have supplementary tables. All right, so please go on Icon after class and cast your vote for your available times for the midterm review. All right, so today we're going to be wrapping up our discussion of the Bernoulli Equation. Okay, the last lecture ran a little bit longer than I expected. We didn't quite get to all of the objectives that I had, so we're going to try to hit those today. So our specific goals for today are we want to understand the function of a Pitot tube. We want to define the energy and head versions of the Bernoulli equation. And finally, we want to use the continuity equation and the Bernoulli equation together. So to sort of to anchor ourselves and understand where we are right now, right? So far in chapter 3, we've really come up with two equations. Those were F equals ma, manipulated a little bit, but applied in different ways. So we said we've got a series of streamlines on each streamline, we have, right, local coordinate system. Let's point these the right direction. S, 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 N, N. And we've derived our two equations. The first is P plus rho GZ plus 1/2 rho V squared is equal to a constant along these streamlines. Okay, so each of these blue lines here can be thought of as lines of constant 1. Then we had our second equation, which was P plus rho GZ plus the integral, or rho is the integral of V squared over the radius of curvature constant normal to streamlines. And so this means is if we took lines that passed through this normal vector and through each of our streamlines, we could draw sort of a network of lines that looked like this. Okay, and so these would be lines of of constant equation 2. So the streamlines and the lines that are perpendicular to them, right, will form this sort of a curvilinear grid, or this sort of net, where at every intersection, the two should form a right angle. All right. And so these two equations, right, apply depending on whether we're looking directly across streamlines or along them. But we have to keep in mind what I stated before were sort of our commandments, if you will, of Bernoulli, or the limitations that are inviolable which are, right, both of them apply to steady flow. Both of them require that we're all right assuming our flow is inviscid, that is, it's not dominated by viscosity. In both cases, we're assuming a constant density, and then the equation has to be applied along a streamline if we're dealing with equation 1, or perpendicular to streamlines if we're dealing with equation 2. So before you apply either of these equations, you have to go through this checklist and make sure that all of those assumptions are at least acceptable. Okay. Now, the rest of what we're doing today is basically demonstrating through example some of the applications that we haven't really gotten to yet. And the first one is this idea of, it's called a Pitot Tube. Yeah.
So about the first limitation.
Yes.
If we were to cross streamlines at an angle, would we have then to find magnitude?
You're saying like this point and this point, maybe, if you were trying. So you would have to do this in 2 steps, right? You would say apply the Bernoulli equation between this point and this point, and then you would apply the second equation between this point and this point. All right. So you have to be cognizant that you're applying the right equation at the right time. There are certain cases. You know what? Never mind. I'm not going to confuse the issue. Just don't cross streamlines with Bernoulli, and don't travel along streamlines with equation number 2. All right. Okay. So the Pitot probe, right, or the Pitot tube, is one of the most widespread instruments that we see out in engineering fields. Any of you ever been, maybe stepping onto an airplane, and if you've looked sort of over at the cockpit, you'll see this little thing sticking out of the side of the fuselage that has a right angle. It looks something like it'll have it'll be this sort of right angle that's sticking out of the airplane fuselage, about 2 inches wide. Anyone ever seen one of those? It usually has a sign that says "Do not step." No. All right. Well, keep an eye out for these. These are what are known as Pitot Probes, and they're instruments used to measure the velocity of the flow past them, and they do that using the Bernoulli Equation. So let's consider a case where we've got maybe we have some flow through like a pipe or between two walls or something where we don't know the velocity and we don't know the pressure of the flow. Okay, so our flow is moving from left to right. We're going to insert two sort of straws or tubes into the flow. The first is going to be at a right angle, and the second one is going to be straight in. And so the flow is going to move past these two tubes, but in the first case, right, it's going to hit the end of the tube head on, and the other, it's going to flow right past the end of the tube. So our question right now is, if we put our points of interest, say right here, and then right here, let's number these point 0, point 1, and point 2. Okay, using the Bernoulli equation, we should be able to figure out what the pressures are at point 1 and 2 in terms of the pressure at point 0. Okay. In other words, if we've got at 0, right, we've got V naught, and we've got P naught, and Z naught is the elevation. So using those symbolically, can we write the pressure at point 1 and point 2? So we'll go ahead and first apply Bernoulli between 0 and 1. This is going to look like is P naught plus 1/2 rho V naught squared plus rho G Z naught is equal to P1 plus 1/2 rho V1 squared plus rho G Z1. All right, initial simplifications we can make. Sort of by inspection, we can see that 0, 1, and 2 are all at the same elevation. That is, Z is the same for all of them. So we could subtract the rho G Z terms from both sides to cancel those out. The second thing is that this tube that's head on to the flow, okay, this right angle tube, is what's known as a stagnation tube. And the idea there is that the flow hits it and it stops. Okay. So at point 1, we would say that the velocity is 0. And so with those cancellations, we can go ahead and say that P1 is equal to P naught plus 1/2 rho V naught squared. And this is what's known as the stagnation pressure. That is the pressure that we would measure if we brought the flow to a halt. And if we looked at this, right, the idea is we've got P1 over here. Let's say we put a pressure gauge at point 1, something we can use to measure the pressure. If we know the density of the fluid, and if we knew P naught, we would be able to infer what the velocity of the flow is. And so that's where the second tube comes in. Okay, we're going to use that second point to figure out what P naught is, and see if we can use those two pressure measurements to then infer the velocity. So if we now apply the Bernoulli equation between point 0 and 2, you can say that P naught plus 1/2 rho V naught squared plus rho G Z naught is equal to P2 1/2 rho V2 squared plus rho G Z2. All right, once again, simplification. We can say they're at the same elevation, so the Z terms cancel from both sides. Anything we can say about the velocity? Well, the idea here is if this tube is designed properly, the flow, the velocity at point 2 should be the same as at point 0. Whereas the stagnation flow causes the flow to stop. This tube that is at a right angle to the flow should allow the flow to move past it without altering the velocity. And so we can go ahead and say, well, V2 is equal to V naught, in which case this 1/2 rho V naught squared and 1/2 rho V2 squared are the same. And we can cancel those out from both sides. And what we're left with then is that P2 is equal to P naught. So the idea here is now if we took pressure measurement devices, some sort of pressure gauge, and if we attach them to point 1 and to point 2, and if we were to take the difference between those two pressures, so if we were to say subtract P2 from P1, we would get P1 minus P2, which is equal to P naught plus 1/2 rho V naught squared minus P naught. So we get that cancellation of P naughts. And now we have a term that only involves the density and the velocity. So if we know the density of the fluid, okay, let's say it's fresh water, 1,000 kilograms per meter cubed. If it's air at standard atmospheric pressure and temperature, 1.23 kilograms per meter cubed. Right? We generally are able to get a pretty good fix on what the velocity is, or what the density is. Then we can go ahead and say that the velocity, 0, is equal to the square root of 2 over rho. Let's extend that square root. P1 minus P2. Okay, and the nice thing is, right, there are lots of measurement devices that allow us to measure the relative pressure between 2 points. We talked about one of them in Chapter 2, or well, Professors Mattia and Eichinger did. Right? What about the U-tube manometer? Right, it's a way of measuring the difference in pressure between 2 points based on the height difference in a column of fluid. And so there's the U-tube manometer. There are things called differential pressure gauges, which will give you a digital readout. Whatever your measurement device is, if you are able to measure this quantity and you can figure out what your density is, then you can measure the velocity, which is really useful. And so these are typically used as backup devices on aircraft to measure airspeed if, GPS drops out or something. The idea there being, right, density is going to change with elevation, but there are pretty good tables that are able to tell us what the density is based on the elevation of an aircraft. So this is the principle of operation of a Pitot probe. And I want you to remember this, understand it. Right? Come to love the Pitot probe because it's something that's going to show up throughout the course. Any questions about this? All right, let's move on to alternate forms of the Bernoulli equation. So first, I'm going to go ahead and write out the Bernoulli equation that we've already seen. Right? P plus 1/2 rho v squared plus rho g z is equal to a constant. So each of these terms has a special name. And these are things that showed up in the text if you read. But the first term here, right, P, is what's known as the static pressure. So, right, this is what we measured with that second of our tubes in the previous kind of example. The second term is what's known as the dynamic pressure. And the third term is the hydrostatic pressure. The idea is if you sum these up, you get what's called the total pressure, which should remain constant. Okay, and we saw in the last problem also that if we took these two terms together, we got what was called the stagnation pressure. Okay, so the thing is that pressure, right? If we were to say pressure is force per unit area, right? It can also be interpreted as the energy per unit volume. So, right, the static pressure is sort of like the pressure potential energy, or 1/2 rho v squared. Looks sort of like a kinetic energy term. Okay, if we were to multiply it by volume, we would get 1/2 mv squared, which is familiar kinetic energy. And so if we divide this through by rho, right, the density, we could say that, right, pressure over density can be interpreted as the amount of energy per unit mass. And so if we go through and we divide everything in here by rho, we'll end up with an alternate form. Looks like this: P over rho plus 1/2 v squared plus gz is equal to, right, again, a constant. And so now this is, right, it's the same equation, it's just been divided through by a constant, but this is what we would call the energy version of the Bernoulli equation. And so we have, this first term is the pressure potential energy. The second one is the kinetic energy. And this third one is the gravitational potential energy. Oops. All per unit mass. Okay, so we'll say per unit mass. And if we add these together, we can say then that we have constant total energy. So this is a way of saying, look, Bernoulli equation is really a statement of the conservation of energy. And under the assumptions we made, no viscosity, right? That's sort of the same as saying it's a reversible process or it's a conservative process. Okay, there's no friction. That means that the total energy is conserved in a fluid. Finally, if we were to divide through by g, this second equation, if we were to divide through by g, we can see from the second term here that what we're going to be left with is something that has dimensions of length. So if we say P over rho g plus 1/2 v squared over g plus z now is equal to constant. This is what we call the head equation. And right, remember in the so when you discuss manometry, the manometer equation with Prof. Mantilla, you talk about how you can describe the difference in elevation difference between a column of fluid as the head. The idea here is we just give these terms different names. This first one is the pressure head. That is, this is how high the pressure would drive a column of fluid in a piezometric tube. The second one is what we call the velocity head. And this third one is the elevation head. And these together sum up to the total head. So I want you to understand that there are different ways of writing the Bernoulli equation, but they are all effectively equivalent. They're just being multiplied or divided by constants. In this case, take the Bernoulli equation, divide it by rho, we get the energy equation. We divide the Bernoulli equation by rho g, and we get the head equation. And you can apply any of these. Okay, yeah.
So if someone told you you had so many inches of water, like water column,
yep,
multiplied by rho g, that's how you get like that factor.
Right. That's the idea. So if you had a case that was like, right, certain problems, let's say we had a tank of water, like often what's called a head tank, actually. Might be a water tower. You had a pipe coming out the bottom. And then spraying upward. So you had now a free jet of water coming out the top. So right, like the intuitively we could probably recognize that the jet of water is going to reach the same height of the water level in the tank. But to show that mathematically, it would be most convenient, probably, just to avoid extra terms, to use the head equation, right? Where we could say, here's the, right, if this is the head of our initial tank of water, we could pick points here. If we wanted to, we could pick a point here, and we could pick a point here, and we could apply the Bernoulli equation. But if we apply the head equation, we wouldn't have to deal with. We could apply the head equation here between that first and that third red dot there, and we could say, okay, we know that we can set the constant or the head equation at point 0, and if we had this one, point 2, we can apply it between point 0 and 2 directly. And we could say, well, we've got the pressure is going to be the same, the velocity in both cases is going to be 0, and so you just solve for z at that point. So this is something that causes some confusion because students treat them as 3 different equations. I just want you to understand that they're the same equation, just written out in different forms and given a different name. Okay, so sort of along the same lines.
Buster?
Yeah.
This equation for head,
Yes.
is this what we were supposed to use for the third homework problem that we were doing today?
Well, again, you can use any of them, right? You can. There are no situations where you have to use the head equation, and you can't solve it using Bernoulli. The best thing the only thing it's really going to do is allow you to save some pencil lead, right? That's.
Yeah, because I was just looking at that problem that asked for pressure head and velocity head. I had no idea what those even were because we hadn't covered yet.
Oh, you actually asked for those terms.
Yeah.
Okay, well then. Cover that, yeah. But it was in the assigned reading. Okay, that is. There's about a half-page section that defines those terms. Okay, so I always have that as a fallback. Yes.
Is the stagnation pressure the same as the pressure at the stagnation point?
Yes. So the stagnation pressure, right? That's why that term is called that. Is because exactly. So right, that's the idea of like a pressure washer. Right, is you induce a very large velocity in a jet of water. It hits right the side of the house with paint you're trying to strip off or something, and because it is brought to a halt, the pressure there increases and creates a very high stagnation pressure.
Shouldn't the velocity be 0 at the stagnation point?
The velocity will be 0 at the
So
stagnation
why
point.
are we including the dynamic pressure to
Because the idea is that, right, so if we go up to our previous example here where we had 0.1, okay, and we had the end of our stagnation tube, the idea there is that we said that P1, right, is equal to the sum of our static pressure at 0 plus a dynamic pressure. And so the idea is that the stagnation pressure is going to be what happens if you bring the velocity to 0, then all of that energy, that kinetic energy, gets lumped in with the potential energy. Okay. So I want to define these things called hydraulic and energy grade lines very briefly. These are more commonly used in civil engineering. than in mechanical engineering, but they're useful to know. So. So an energy line, okay, can be thought of as, if we're looking at our head equation, okay, an energy line is basically plotting out the the total head of a system. So if we take and so this can be thought of as the elevation of a series of stagnation tubes in a flow. And this is probably a confusing statement. I'll clarify it in a moment. And the second one, right, the hydraulic grade line, is the elevation of a series of static pressure tubes in a flow. So in other words, if we were to, I'm going to scroll back up here for a second. If we were to take this situation again, let me go ahead and copy this and bring it down so that we aren't scrolling a ton. Ooh. Paste. There we go. Okay, so right, so tube 1, right, a stagnation tube. If we were to connect this to, if we were to allow if instead of having a pressure probe at the end of it, this were to be full of whatever fluid, as if it were like a straw. We took a straw, bent it 90 degrees, stuck it into a flow. The idea is that the fluid that is flowing past is going to occupy the tube and fill it up to some height. Okay. Now, the height of that fluid in the tube is going to be the pressure head plus the velocity head plus the elevation head. All right. And so that's going to be indicative of the total head in the system. And if we were to, and so that is going to be the energy line at this point in a system. Whereas the hydraulic grade line would be if we were to allow the same thing to occur here. If this second tube were to be open to the flow, it's going to fill up to a level that is lower. So let me quickly draw a little schematic here. Let's say we've got, let me make this bolder. Okay, so let's say we've got a tank, a fluid that empties into, okay, a really large diameter pipe that then narrows into a smaller diameter pipe before ending in a jet that aims upward. And with water spraying out of that jet. Okay, so if it's full to a level like this initially with water's flowing through the pipe and exiting through this jet. There's a much better version of this drawing in the book, but this should suffice for now. Idea is that the at this side we could say that the gauge pressure, that is the pressure relative to atmospheric pressure, is 0 here, and we could say the same thing here. That the pressure is equal to 0. We should also be able to say, we'll get to this actually in just a moment, right? That we'll have some non-zero velocity at this section of the pipe, and as the diameter of the pipe narrows, what's going to happen to the velocity? Okay, intuitively, it's going to get larger. Okay, so we're going to have, we'll say that we have here a larger velocity of flow through this section of the pipe. Okay, so the energy grade line versus the hydraulic grade line. Let's go ahead and draw a set of axes. Okay, so we've got the length along our flow, and up here we're going to have the head of the system. The energy grade line is, like I said, this is basically plotting out the total head of the system. So it's just going to be a constant that moves along, or that is equivalent to the highest point in our system at atmospheric pressure, or equivalent to the height that a jet of fluid would reach if it pointed directly upward. So the energy grade line. The only time that the energy grade line will change in elevation is if our system has some sort of frictional losses in it. Okay, so in that case we wouldn't be able to apply the Bernoulli equation, but the energy grade line as a concept is still valid. The hydraulic grade line is going to be coincident with the energy grade line over here, and then it is going to drop down here, it is going to drop lower here, and then it is going to drop lower still here. Okay, and that is because this is the hydraulic grade line. That's because the hydraulic grade line, if I zoom out just a little bit, is a sum of these two terms. So the difference between the energy grade line, and the hydraulic grade line is always going to be the velocity head. That is, it's going to be that 1/2 v squared over g is always going to be the difference between these. So conceptually, the idea is as the flow goes faster, more of your potential energy due to pressure and due to elevation is going to get sort of co-opted to turn into kinetic energy. It's this trade-off, this classic trade-off between potential and kinetic energy. But as more of the total energy of a fluid is moved to that kinetic energy column, the elevation of your hydraulic grade line is going to decrease because that is reflecting the total potential energy in the system. I don't really have time to spend doing a lot more with grade lines, but I just want to introduce you to them. Please check out the section of the book that summarizes them for a little bit more clarity. What I want to do with the last 10, 12 minutes is at least get started on an example that involves combining the Bernoulli equation with what we call the continuity equation. So we're going to formalize this a little bit in the next chapter, this idea of what we call conservation of mass. But at this point, we should be able to intuitively understand that, right, if we have, just as in the previous example, if we have sort of a pipe that changes diameter, right, it's probably not. Basically, the flow in through the left and the flow out through the right is going to contain the same amount of mass per unit time. Right, the mass flow rate in has to equal the mass flow rate out, which is the equivalent of saying, right, that rho times, if we've got 0.1 and we've got 0.2, that rho 1 times V1 times the cross-sectional area of the pipe at 1 is equal to rho 2 times V2 times A2. And if we're dealing with the same fluid, and if the assumptions of our, that is what I want to see, and if we're dealing with the same fluid and the assumptions of the Bernoulli equation hold, that is that rho is constant, then we could cancel that out from both sides. And we could say that basically the volumetric flow rate in is equal to the volumetric flow rate out. Okay, we're going to leave that right here as our definition of what we call the continuity equation for now. Like I said, we'll develop this a little bit more rigorously in chapters 4 through 6, but this should hold for now. When this becomes useful is in cases where, one moment, I gotta copy, I'm gonna black this out for just a second. Forgot to copy this figure over earlier. Bear with me for one moment while I grab it out of my notes. Okay, so here's the example problem that this new equation, the continuity equation, is going to help us solve. Okay, and this is one that we might not quite finish, but if we don't, I'll post the completed solution up on Icon. So what we would be looking to find in a problem like this is, let's say we've got one fluid on top of another fluid in a tank that has some pressure greater than atmosphere. And we've got points that we'll number. Okay, 1, 2, we're going to ignore that point. We'll call this point 3. We'll call this point 4. So there are a couple of new things in this. First is we've got dissimilar fluids. Okay, so we've got something with specific gravity of 0.7, which is the equivalent of saying that in fluid 1 here, rho 1 is equal to 700 kilograms per meter cubed, and fluid 2, rho 2 is equal to 1,000 kilograms per meter cubed. So that's approximately something like motor oil sitting on top of water. And then the second thing is, as we just had in our little informal derivation previously, we've got a change in the diameter of the pipe. So you know what, rather than going through rigorously through a solution right now, let's just step through it in broad strokes so that we can understand, at least from beginning to end, what we would be doing to solve this problem if someone came along and told us to find the pressure at point 3. Okay, so we might say this is a problem for Bernoulli. The other assumption we're going to make here is that this tank here is very large, right? Which means that we can assume that all of the velocities in this tank are approximately 0. So step 1 might be, if we said our solution process for this problem would be, all right, first we might say apply hydrostatics between point 1 and 2. Okay. In other words, we would say, right, we know pressure at point 1. It's specified as pressure being 20 kilopascals, 20,000 pascals. And we could say that, right, the pressure 2 then is equal to the pressure at 1 plus rho 1 times g times that 0.5 meters that specifies the elevation difference. Okay, so we can calculate the pressure at 2. Fun little fact here, right? We could also do Bernoulli, because if the velocity disappears from the Bernoulli equation, it just turns into hydrostatics, or the manometry equation. Okay, at point 2, where we have this interface between our two fluids, the idea is if our fluids are not moving, we should have equilibrium between the two. That is, at that interface, at point 2, the pressure in fluid number 1 and in fluid number 2 will be the same. Okay, because if we have equilibrium, fluids at 2, this is the equivalent of saying, if this is our division, we've got fluid number 1 on top, fluid number 2 below. This is a terrible drawing, I apologize. And divided by this interface, it's simply saying that, that fluid number 1 is pushing down on fluid number 2 with an equivalent pressure. The fluid number 2 it's sort of like a action-reaction statement. Okay. So we're just going to say that basically P2 equal in both fluids. And like I said, I will post a more detailed solution to Icon, so if you're not following the details here, they'll be included. All right, step 3 would be the Bernoulli equation between point 2 and, this is going to be a little bit of a departure from the past. We're going to skip point 3 for now and apply it between point 2 and point 4. Okay, so at point 2, we know the pressure, P2. We know the velocity, 0, and we know the elevation. At point 4, we know the pressure. The pressure is 0 because it's the jet exiting to the atmosphere. So we say P is equal to 0 down here. We know the elevation difference, at least, between points 4 and points 2, 1.75 meters. We don't know the velocity. So we have one unknown, and we have the Bernoulli equation, which allows us to, we assume that there's a streamline connecting point 2 to point 4, That allows us to then find the velocity at point 4. Why wouldn't this work at point 3? Why can't we just do Bernoulli equation between point 2 and point 3? We don't know the velocity and we don't know the pressure, So we have two unknowns. So what we're doing here is we're finding the velocity at point 4, and then we say, all right, if we know the velocity at point 4 and we know the diameter of the pipe at point 4, we can figure out how much volume per unit time is flowing out through point 4, and we could say the velocity at point 3 is not going to come from the Bernoulli equation, but from, instead, this equation right here. So we would use this process to find V4, and we would apply the continuity equation then between point 4 and point 3, which would allow us to say, that V3 times, let's say instead the V4, which is known from the previous step, times the cross-sectional area of the pipe at 4 is equal to the velocity at 3 times the cross-sectional area of the pipe at 3. In other words, this would be V3 is given by V4 times A4 times A3, or the ratio of the cross-sectional areas of the pipe. Okay? So now we know V3, and now we can apply the Bernoulli equation between, we have two choices. We could say now Bernoulli between, we could go between either point 4 and point 3, Or we could do the Bernoulli equation between points 2 and 3. Because the only unknown at point 3 now is the pressure. And so we can use the Bernoulli equation from either side to solve for the pressure, or a single unknown. So I'll post this detailed solution on Icon. This is the last set of material to be included in the midterm. Right? Reminder, please go on Icon. I'm not sure I enabled the link quite yet, so go on Icon like in a few minutes and submit your availability for the midterm review. Okay, thanks guys. See you on Friday.